The next leg on our journey toward proving the optimality of Huffman codes is a lemma that I'll refer to as the siblings lemma. A lemma on siblings, quote unquote. And it says that for any PMFP, and it's just P is our usual P1 up to Pn, there exists an optimal binary prefix code with two siblings. So there exists an optimal binary prefix code. We're focusing on the binary case. Binary prefix code with two siblings. And what does that mean? So such that two of the longest code words satisfy the following two properties. So A, first property, they have the same length. So two of the longest code words have the same length. And further, property B, they differ only in the last bit. So two of the longest code words have the same length. Color switched. And they differ only in the last bit. In other words, they're the same for all the bits 1 up, 2, 3, so forth up to the last bit in which they are different. So let's give an example. So the claim is that there exists an optimal binary prefix code with two siblings. And let's just illustrate by a little example what this property means. So this will refer to as the sibling property. This code has the sibling property if it has these two such code words. So let's say we have some prefix code, I don't know, 000, 001, some other stuff, and maybe 1000, 10100, 10101, 10110, 10111, say something like that. Now, does this have two siblings? So this is the sibling property, and let's check. So here, these four guys at the end, assuming that we've, assume all this stuff is prefix in here, and let's suppose that we have ordered the code words from shortest to longest, then these four guys down here are the longest code words. And are any two of them siblings? Well, they're two, we need two of the longest, have the same length, and differ only in the last bit. And they all have the same length. And here, these two are the same length and differ only in the last bit. They're the same in bits 1 through 4. And likewise, this pair as well is also a pair of siblings. Same in the first 4 and different in the last. So in fact, the property is sort of doubly satisfied for this little example, but we only need there to be one pair of siblings for this property to hold. This example just happened to have two examples. If there were, it would still be true if, for example, this were like a 1 here or something like that. Okay, but let's make it a 0 since that's what I said originally. Right, yeah, so just to be clear on that point, just since I said it. So if this were a 1 instead, then these would differ in the first 4 bits, and these two would not be siblings anymore. But these two still would be. So the property would still be satisfied. Okay. Now, what is the proof of this? So we made this claim. Let's prove it. Proof. So we're making a statement about the existence of a certain optimal code, optimal prefix code, and we have our nice existence lemma up here that guarantees that for any PMFP we have some optimal prefix code. So let's start out with some optimal. So let's C be optimal prefix, and we know there's at least one, and all of the optimal prefix codes they're optimal for P, they have some lengths, and let's think about the sum of their lengths. This quantity, they each have, the sum of the lengths is something for each of them. And let's choose one out of all the optimal prefix codes for P. Let's choose one for which this sum is minimal. So let's choose C such that this and the sum of the lengths is minimal. Now note, this is not equal to the expected code word length. The expected code word length is the sum of the lengths times the probabilities. There's no probabilities here, right? Because, optimality is saying that L is minimal. Optimality is already guaranteeing us that this expected code word length is minimal, and we are stipulating further that the sum of the lengths is also minimal. Okay. Now, we have chosen this C, and I claim that in fact it has the sibling property. It is such a code. It has these two properties A and B. So let's prove that. Let's first consider A. Let's prove that it has property A. Two of the longest code words have the same length. And in order to prove that, let's do a proof by contradiction. Let's suppose not. Suppose A is not true, and we will obtain a contradiction. So if A is not true, then that means that there are not two longest code words with the same length. Or in other words, there is a single code word that's longer than all the others. So in other words, so if we were to say that the lengths were ordered in this way, we could permute the p's or something to make the lengths ordered, just to simplify our notation a bit. So suppose the lengths happen to be ordered like this, and then ln would be actually strictly greater than all the others. So that if A is not true, that implies there is one that is strictly greater. So for example, in our example over here, if these were all ordered in their lengths, then there would be an additional bit or more on this last guy. So maybe there's an extra 0, or it could be 0, 1. But let's just say it's an extra 0. Now we're going to construct a new code. Our plan of attack is we're going to construct a new code that is going to somehow contradict these suppositions, the fact that C was an optimal prefix code and it had this property, the minimality property. So C, let's denote the code words of C, W1 up to Wn, and let's construct a new code in the following way. Let's let C prime have all the same code words, W1 up to Wn minus 1, and then it's going to have Wn prime for its last code word, where Wn prime is obtained by just erasing the last bit from Wn. So if this was Wn here, then we would just drop that last bit, and that would give us our code word Wn prime. So Wn prime, we could, there would be Wn prime and then some additional bit, maybe, I don't know, I'll call it, alpha or something. That would be equal to Wn. Alpha here is in our code alphabet. So the length, so all of the lengths are the same except for ln prime. So if the lengths of our new code are li primes, then they're all the same. They're all equal to the original ones, except ln prime equals ln minus 1, because we dropped one bit. And all the others, all the others are the same. Li equals li prime for all I equal 1 to n minus 1. Now, we would like to obtain a contradiction. That's what we're aiming for here, to show that A is in fact true. And so how can the existence of our new code contradict something here about C? Well, we'd like to somehow show that C prime somehow contradicts this. So let's first say, let's see if we can show that it's a prefix code. So C prime, is it prefix? Well, so we dropped our last bit here, but all the other code words are the same. So we know that there's no pair of those, no one of those is a prefix of another. So we just need to check this guy. So if Wn prime, if our new code word is a prefix of another, Well, we know that it's at least as long as all the others. So that would mean that it would have to be equal to one of the others, right? It would have to be, since it would be the same length. Like, for in this example here, this would be the same length. In order to be a prefix, it would have to be the same length or shorter, and it would have to be the same length since it used to be longer than all the others. And if it's the same length and it's a prefix, then they're equal. So, but if they're equal, then the other guy must have been a prefix of wn. It must have been a prefix of the original wn, and that would contradict the supposition that C was a prefix code. So we know that our new wn prime is not a prefix of any of the others. Are any of the others a prefix of him? Well, suppose one of them were. Suppose one of these were a prefix of our new wn prime. Well, then it would have also been a prefix of the original code word of wn. And again, that would contradict the prefixity of our original code C. So therefore, we know that C prime is in fact a prefix code. So let's write that down. So we have C prime is prefix. Now, what about other properties? Let's see, optimality. Well, we've only shortened code word length, so optimality looks very good. Optimality is the sum of the lengths times the probabilities, and if we shorten the lengths, then our expected code word length has got to be certainly less or equal to what it used to be. So we are certainly optimal. We have optimality. And in fact, it would be strictly better than C if Pn were positive, and that would already be a contradiction, and we would be done in that case. But if it so happens that Pn is 0, then we would not yet have a contradiction. C prime would have the same expected code word length as C. But to save the day, so the case of Pn equals 0 is why we had to include this extra condition here. And this extra condition saves the day because we supposed that C had a minimal sum of lengths. And yet our C prime, if we sum its lengths, sum of the lengths, that equals the sum of the original lengths minus 1. Because they're all the same except for ln prime is 1 less than ln, and that contradicts the supposed minimality of the sum of the lengths for C. So this is a contradiction. And that implies that A is in fact true. Excellent. So now we still have to show that B is true. We did A. Let's do B. So B, we'd like to say that our chosen C here, we're still sticking with the same C. We let C be an optimal prefix with minimal sum of the lengths. The sum of the lengths is minimal. And we need to show that now it also satisfies B. We know it satisfies A, so we at least have two code words of the longest ones that are the same length. And to show B, let's again do a proof by contradiction. So suppose B is not true. And we will again obtain a similar contradiction. All right, so to make this little discussion concrete, let's let K be the length of those longest code words. We know there's at least 2 of the longest code words, CWs. Now, what is B saying? B is saying that of those code words of length K, 2 of them differ only in the last bit. And if B is not true, or actually let's restate that. So B says that 2 of these length K guys differ only in the last bit, or in other words, that there exist 2 of length K that are the same in bits 1 up to K minus 1. So that's another way of saying the same thing. They're the same in bits K 1 up to K minus 1. And if B is not satisfied, then that means there do not exist 2 of length k that are the same in bits 1 up to k minus 1, obviously. Or in other words, no 2 code words of length k are the same in bits 1 up to k minus 1. Or yet again, we can restate that as any 2 code words of length k differ somewhere in the first k minus 1 bits, that is. So, so for example here, let's say these are our length k guys. So b is not true. Then any 2 of these longest code words differ somewhere in the first k minus 1 bits. So let's actually change this so that that's actually true. Let's make our example illustrate that property. So let's make it something, I don't know, something like this. I think that works. And so now that we're in this situation, let's do something similar to A. Let's construct a new code, C prime. So we have our code C. Let's construct a C prime. And let's do it in the following way. So we have these, so in this case it's 4 guys that are all of length k, and here k equals 5. K equals 5. So let's make our new code by just picking any one of these, and let's just drop its last bit, sort of just like before. So let's maybe pick this guy here. We'll drop its last bit, and our new code will be all the original code words except this guy without the last bit. And now let's follow the same plan as in A. That seemed to work well. So let's try to show that our new C prime is a prefix code and it's optimal. Well, clearly it's going to be optimal for the same reason as before. We've reduced the length, so certainly it's going to be optimal. And also, since we cut down the length of one of them by exactly 1 bit, then we're also going to have this property. The sum of the lengths of our new code is going to be the sum of the original lengths minus 1. So we got optimality in this, and we just need to see that it's prefix. And if it's prefix, then we're done. Then we would have a contradiction, just like in A. So let's see, is this new thing going to be prefix? So I'm just illustrating it with this example, just to make it sort of concrete. But this argument holds in general. So why is this new code prefix? Well, so all the other code words, all the unchanged code words are the same, and they satisfied the prefix property. And so we just need to check that this guy is not a prefix of any of them, and none of them are a prefix of him. So first, let's suppose one of the others happen to be a prefix of this guy, and now it's just the first 4 symbols. We've dropped the last one. Suppose some other code word was a prefix of this. Well, it can't be one of the longer ones. They certainly can't be a prefix of it. So if one of these shorter ones is a prefix of it, then, well, they would have been a prefix of the original thing, just like before in A. And that's a contradiction because we know that C was a prefix code. So it can't be that any of them were a prefix of him. Now, could it be that he is a prefix of somebody else? Well, first let's check these, the length k guys. So if he is now a prefix of one of the length k ones, then that would mean that he's the same in the first k minus 1 bits because he has length k minus 1. That's exactly what it means to be a prefix of another code word. So, but if he's the same in the first k minus 1 bits as one of these other guys, then that contradicts our assumption that no 2 of the longest code words were the same in the first k minus 1 bits, right? We suppose that was our supposition. We supposed that B is not true. So we suppose that any pair of these, in particular this guy and any of these, differ in somewhere in the first k minus 1 bits. And so he could not be a prefix of any of those. Now, could he be a prefix of any of the others? Well, they're all shorter than him, or equal length. So he would have to be a prefix of one of the ones of equal length. And if he's a prefix of something of equal length, then in fact they are equal, and that other one would have been a prefix of, is also a prefix of him, and would have been a prefix of the original unchopped code word, including that last original bit. It would have been a prefix of the code word in our original code C, And that would be a contradiction because C is a prefix code. All right, so we know that our new code satisfies the prefix property. And as we already saw, it's optimal, so it's prefix. I'm re-annotating our notation from A. Our C prime in B is prefix, it's optimal, and it satisfies this property that the sum of the lengths is strictly smaller, contradicting our supposition that C was optimal prefix and had minimal, the sum of the lengths was minimal. So therefore, just in the same way, this is a contradiction. And so B must also be true. Okay, so that's it. So we chose this C, and we showed that it satisfies these two properties, and therefore we know that there exists such a code with the sibling property. So this is our sibling property code right here. And just to point out one thing here about the proof, the reason why we had to do this is because if some of the probabilities could have been zero, and in that case, even though you're shortening the length of one of the code words, like here we were shortening this guy's length, if the corresponding p were 0, that wouldn't necessarily, that would not strictly improve the expected code word length. So that's why we needed this extra sort of condition. All right, so that proves the siblings lemma on the existence of an optimal code with the sibling property.